Hello, dear all conference participants and organizers. It is very nice to take part in this international conference. I am Raminta Venslavaviciute, PhD student. I study at Vilnius Gediminas Technical University, and my doctoral dissertation topic is multi-stage nonlinear analysis and optimization of stainless steel frame. Depending on this topic of a dissertation, I have prepared a study and a short report on the theme Weight Optimization of Stainless Steel Build-up Structural Elements. So feel free to ask questions after presentation. I will try to answer them. At the beginning, I would like to briefly start reviewing the literature sources associated with stainless steel. Stainless steel as a structural material began to be explored in the late 1980s. However, due to expensive steel extraction technology and lack of methodology, there is a small number of publications and a variety of research. Also stagnation in compiling the calculation methodology. After 30 to 40 years, due to several times the decrease in the cost of stainless steel production, a particularly high level of activity and interest in stainless steel research is observed. The big peak is currently being observed in its 20th year. With the advancement of research technologies, it is possible to develop a stainless steel calculation methodology that is accurate as possible with the support of experiments and analytical research safely and reliably. Moving on, this chart represents literature sources that clearly show the beginning of stainless steel research and the boom of 21st century audiences. This was due to the favorable development of steel production technologies and the resulting fragmentation of research methodology, which opened a niche to continue to study stainless steel and expand the use of the steel in the construction market. Stainless steel as building material with the most useful properties has long been used in extreme cases. Stainless steel as a material consists of many different metal alloys. It is very convenient to choose the one that is best suited in the prevailing environment and during construction and installation. Austenitic and duplex are most widely used in the structural steel selection and are currently widely used, especially in design of structures such as built-up columns, tetrahedral trusses, and frames. For more specific, austenitic stainless steel is usually used in structural design of rural, urban, and light industrial sites, marine sites. Duplex steel is used in structural design of structures in marine and other aggressive environments, also used in many onshore exposed conditions. And finally, ferritic stainless steel is usually used in chloride-containing environments. Moreover, optimal and efficient design is extremely relevant and often desirable when designing commercial and industrial constructions. The benefits of structural optimization are best reflected in the construction of large spans and/or extremely high structures. In both cases, the arrangement of a structural elements is as economical as possible when the critical stresses are applied. Because of their layout and profiles, the stability, strength, and weight of an entire structure depends on it. Efficient and optimal arrangement of structural elements becomes even more important when stainless steel is used instead of carbon steel. With this in mind, optimal structures are becoming a top priority criterion when using stainless steel in high-span structures. With the increasing use of variety metal structures, it is now very important to design rational and/or optimal structures. In order to properly define the mathematical algorithm, the optimization method must be selected according to the type of variables. Another important aspect in the use of optimization algorithms is sustainable structure and durability. This is very important in order to reduce the production costs of structural elements and reduce the emission of carbon dioxide emissions in the environment. This makes the designs environmentally friendly. As is known, the structure of high-rise buildings has the greatest impact on the environment, so the use of optimization algorithms is particularly relevant, especially for materials such as stainless steel. The aim of this paper is to analyze a realistic model of structural elements of stainless steel, which plays an important role in the analysis and design of steel-framed structures. Structural element modeling and optimization using stainless steel in case of build-up column can contribute to existing research on stainless steel. The object under consideration is a stainless steel build-up column, which is classified as a typical structural element. The purpose of this optimization problem is to perform the minimization of the weight of a selected built-up column when the height of a column and the load acting on it are known. The built-up column is considered with two different types of cross-sectional chords. At the first with circular cross-sectional chord and then with elliptical cross-sectional chord. The structure to be analyzed have to satisfy the strength and the stability constraint, as well as the in-plane and out-of-plane restrictions. These conditions are accepted in the optimization problem as constraints in order to find the variables. Restrictions also include the determination of a class of cross-sections used at the design condition defining the relationship between the column chord and the diagonals. Here standard design optimization model with equality and inequality constraints, where variables are described as continuous, and a general model for optimum design. The solution of optimum design problem is given from equation that requires the selection of appropriate stainless steel sections that the weight of a built-up column becomes minimum while the constraints are satisfied. Because of the design problem becomes a continuous programming problem. Such a problem can only be solved by mathematical programming. It is very important to mention that this is a non-convex optimization task, and one of the ways to solve it is a genetic algorithm. According to this, genetic algorithm is the best choice to provide an effective solution to the continuous optimum design problem. The objective is to find a minimum cost function of build-up column weight. The defined problem shall be worded in such a way that by means of a genetic algorithm, optimal variables are found that satisfy the conditions and restrictions. In this parametric analysis, two different types of cross-section, circular and elliptical, are used for the stainless steel build-up columns. First of all, when the circular cross-sections are used, the axial load and bending moment are gradually applied to the selected build-up column. Then the same load and analysis is applied with elliptical cross-section. For case A, the parameters that are selected during the analysis are distance between column chords, acting axial load, and maximum bending moment at the middle of a build-up column. Chosen variables: outer radius of a cross-section of a built-up column, wall thickness of a cross-section of a built-up column chord, outer radius of a diagonal cross-section of a built-up column, and the wall thickness of a cross-section of a diagonal. For case B, the following 6 variables are taken as task variables, which are obtained as continuous. The most important variables are cross-sectional parameters of a column chords and diagonals, such as the cross-sectional radius and the cross-sectional wall thickness. Also used as variables are the angle of the inclination of a column diagonal with a column chord and the distance between the centers of the chords. The number of diagonal elements also depends on these variables. A constraint is introduced for each variable. The cross-sections of a column chord and diagonals are limited by cross-sectional classes, in which case the cross-sectional parameters sought must meet the requirements of a second cross-sectional class, limiting the maximum possible ratio between chord and diagonal according to the design conditions. Also, the angle between the chord and the diagonal is limited to between 30 to 60 degrees, depending on the height L of a builder column. There is a constraint of a minimum and maximum distance between the chords of a column. Because of two types of cross-section are used in the chord calculations, all the listed initial data and variables are associated to a circular cross-section respectively in the case of oval cross-section. At the start of a parametric analysis, the build-up column is loaded with a concentrated axial load and the bending moment is set to 0. The next step in parametric analysis is to include in the analysis a fixed maximum bending moment in the middle of a column. The principle of analysis analogous to the previous one. The axial load is gradually increasing and the space between columns chords is changing. The results show that the optimum weight of a build-up column depends on the bending moment and the distance between the column chords. The final step of parametric analysis is slightly different. According to influences of bending moment in search of an optimum build-up column weight, an analysis is performed where the concentrated axial force is constant, but there is a gradual increase in bending moment in the middle of a column. The results of analysis showed that as the spacing increases, the optimum column weight decreases faster. During parametric analysis of a build-up column with 6 variables, we can see the difference between build-up column with round chords and elliptical chords. The first chart perfectly shows the dependence of the acting axial forces and the distance between the chords of a build-up column. In this case, this chart shows that when the load is increasing, the distance between the stripes is increasing. In build-up column with round chords, the second diagram shows clear dependence between the acting axial force and the angle between the build-up column elliptical chords and the diagonal. The chart on the left side shows clear dependence between axial load at the constant bending moment and the distance between the centers of the chords. Visible line are chord dependencies. However, distance between elliptical chords is directly dependent on active loads. On the other hand, the distance between round chords is not affected by this load. Similar dependencies is visible at the chart on the right side. As we can see, the distance between the chords of a built-up column with round chords is not directly dependent on the acting axial force and the acting moment. This cannot be said about the elliptical chord. This diagram shows a marked correlation between the distance between the elliptical chords and the operating load ratio. These dependencies is important in finding a minimal column weight. Because of the weight depends on the number of build-up column diagonals, and this quantity depends on the distance between the chords. To sum up, the computational results showed that the chosen optimization model and genetic algorithm allow efficiently obtain the column of minimum weight where the variables are column chord and diagonal cross-sections. Taking into account the results obtained from a parametric analysis, it can be stated that the discrete problem should be solved further in order to adapt the assortment of profile sections. The obtained result confirmed that these type of structural elements of the steel in question are needed to develop a more efficient design of stainless steel structures in the design method, thus contribute to its wider use in construction. During the literature review and searching, the most surprised was the wide use of stainless steel. It is widely known that such steel is used in structural constructions for a very long time. However, the most surprised the use of such steel is in cosmic spaceships. This once again proves that advantages of stainless steel compared to normal carbon steel or others. Here I have to mention the basic and most important sources of literature on which I have prepared this research. Thank you for your attention and your time.